So I don't know if everybody was there when I first arrived. I said that I was a user experience specialist, so I'm more interested in the UX side of things than the technical side. But and I think in machine learning models there is a huge impact on user, especially when you think about classification models. There are issues of fairness and discrimination. So I wanted to talk about that, but I used mostly one article that has been written by D'Alessandro, O'Neill, and Lagata, entitled Consensus Classification, a Data Scientist's Guide to Discrimination-Aware Classification. The idea is they present a model of how to first check that a model is fair or not, and then they suggest some tools to make it more fair. So what's at stake with algorithm fairness is that we live in a world that is not fair at all. We build the models on data that is taken from the world, and so this data has inherent bias, like has inherent unfairness and discrimination issues. And machine learning is used more and more for a wide range of things like credit worthiness. In the US, this is huge. Recruitment, health, college ranking, advertising, employee evaluation, justice decision. So in all these areas, sorry? More, yeah, no, there is three dots at the end, so it's just like, but it's just to cover, like, it's covering a wide range of areas, and in all these areas, there are potential for discrimination and huge impact on individuals and at scale society. Like it's the user experience, but also the health of the whole society that is at stake here. So the idea is how to ensure that the results of an ML algorithm are fair. Um, yeah. Yeah, I will use the definition that the author used in the article, but obviously this is a huge debate. So I won't get into this debate tonight, but you're right, absolutely, absolutely. There is a huge range, and it's a philosophical debate basically. So that's so yeah. First is case studies and definition. So we will work with one definition. It's not like maybe not even well accepted, but at least it's a narrow definition, and we can work with it. Discrimination sources. So we will examine in more details what are the causes of discrimination in algorithm, in machine learning algorithm. And then in the third part, we will go through a number of tools that data scientists can use to try to design fairer models. So definition, first case study, predictive policing. So maybe you've already heard about this kind of algorithm. The idea is that you want to predict where the next crime or crimes are going to happen, so you can deploy ahead of time the police force in the right neighborhoods, in the right location, so they can catch the criminals. So it sounds great, it sounds perfect, especially in a context where police forces are limited, budgets are small and getting smaller, so they can't cover all space in a big city, so they want to know where the crimes and the criminals are going to be. The issues when these models are built is that they are built based on existing data from police, and we know that there is an history of racial profiling for some police. I'm basing this mostly in the US, so that might not apply I don't know if it applies or not in Switzerland, but it's definitely the case in the US, and even in France, some studies have shown that there is definitely racial profiling, and this is present in the data, so this is present also in the predictions. Violent crimes for a number of cities are too few and far between, and they are not enough in and of themselves to make a good model. So what they do is that they add an, yeah. Uh, I'm just getting to that, if you don't mind. Yeah. So yeah, there is there is not enough violent crimes to make a good machine learning model. So they add nuisance data. Nuisance data is when you someone break a window or spray a tag on a wall or something like that. There is no physical injury to humans, so it's the difference is that the distribution of violent crimes and distribution of nuisance are not always the same, and nuisance are far more likely to be biased than violent crimes. And it's also related to the next, the self-perpetuating loop, is that the sources are different. Violent crimes, because there are injuries, there are people involved, they are calling the police to complain, right? Police doesn't have to be there to see the crime. Nuisance, most of the sources of nuisance is police officer observing someone doing something, at least for convictions, because otherwise, if you don't see someone breaking a window, it's very hard to catch actually the person who broke the window, right? So that's the reason why there's a self-perpetuating loop, because more police presence means they are observing more nuisance crime, and so they are reported, and then they are entering the data, and it becomes this self-perpetuating loop. Whereas for violent crimes, if they are not there, well, there are always people calling in violent crimes, but there are not people calling in when there is just a nuisance crime in other areas, I mean, when the police is not there, and it's not there because the algorithm has said, well, there's no violent crime, or there's nothing happening, or there won't be anything happening in this area. So that's the issues that we can see in predictive policing. The next case study is Chronos. It's the idea of, in HR, human resources, to predict the productivity and churn of job candidates thanks to personality tests. So, when you receive a job candidate, how do you know which one is going to be the best one to hire, which one is going to be the most productive employee, future employee? Once again, training data is based on former recruitment policies, and former recruitment policies might have bias, conscious or unconscious, against women, for example, against minorities, and so on. There is an incomplete feedback loop. So you can't detect the false negative, because the candidates who will not have a job because the algorithm said is going to have a low productivity. You have no way of knowing what is going to be its actual productivity, because he has not been hired. So you can't check on this, and you can't detect that. So there is no way to correct, in a way, the model based on this. And then that's another research issue, that personality traits are actually a poor predictor of productivity, according to some social research, but they indicate mental health issues. Mental health issues are themselves shouldn't be discriminated against at least in the US, it's illegal. But these personality tests actually might be a way of, I don't know if it's a way of bypassing this discrimination by screening off people with potential mental health issues without saying that they screen off people with mental health issues. Like, that could be something else. So the idea here is that which variables are we using? Do they actually match what we want to prove? And we are going to get back to that later. Kronos? It's in and of itself a company, Kronos. It's an HR company that provides services to major other companies in screening candidates and so on. So I should have given you the microphone, but yeah, no, you're absolutely right. There was, and I think they gave up on the algorithm in the end, yeah, because of this issue. So this is not exactly the same. It's very specific on personality test, but yeah. Yeah. There is, yeah, there is, for the personality test specifically, there is something that is not specifically ML, but in this case, it's used as ML. And the idea is, and we'll get back to that, but when you have, when you design a system, which variables are you going to use? And they have personality tests available, they have other variables available. They still chose to use personality test. So definitions. So we are using this definition that is like limited for this presentation, and there are other definitions possible, and I don't want to get into this debate tonight. Protected class or attribute in the US, race, color, religion, sex, national origin. So these are defined by law. That's squared. We could imagine other attributes, but that's protected by law. And we define discrimination by differential treatment on the basis of membership in a protected class that disadvantages that class. So that's what we call disparate treatment when we are going to go into the assessment of machine learning model. There is also, that's the most obvious discrimination definition. The second one, treatment on the basis of inadequately justified factors, not protected attributes, but disadvantages members of a protected class. That's disparate impact. So you don't know that you're targeted, you don't have the data to say this one is a male, this one is a female, but when you take the results of your algorithm and you screen them and you realize actually females are really disadvantaged, for example. So that's disparate impact, even though the criteria male or female isn't present in the data. So discrimination sources. So just maybe I went a bit too quickly. Three main sources: the process of data science itself, the data, and the misspecification in the machine learning model. So that's from the most obvious to the maybe least obvious sources of discrimination. So the process of data science, A typical process: business understanding, data preparation, modeling, evaluation, deployment. I guess you're all familiar with this process. The issues there is low involvement of domain experts. So maybe the data scientist doesn't understand that personality tests are actually a low predictor of activity. And they say, oh, I have some nice data, I will include it in my model. No audit of the data at exploratory stage. When you do normally exploratory stage, you analyze your data. You should check for existing discrimination in your data. And then no test afterwards for discriminating behavior of the algorithm. So that's part of data scientist practices that should allow for less discrimination. Discrimination sources in the data, that's what we always talk about and hear about. Data reflects systemic biases that exist in the real world. So there is, we all know about discriminations, and the data reflect that discriminations. So we will reproduce that discrimination when training the models. There is also an issue with sample bias. I think you all heard about examples of under or overrepresentation of a class with protected attributes. I don't know if you remember, but there was an algorithm trained on images of people of beauty competition, women beauty competition. And the most beautiful women were all white, because all the training data was mostly white. And when you submitted a person of color, it was not judged beautiful. Jack assists for you to use the mic.
So there's another example from IBM where they had a product which was a facial recognition API. Mm-hmm. And I think on white men, it got something like 99 point something % accuracy.
Yeah.
Sort of what you expect on ImageNet. But then as you go from white man to white woman to black man and all the way down to black woman, it drops dramatically to something like 60% accuracy.
Yeah.
And this is potentially huge impact, because if you want to use such technology as a protection mechanism or whatever in say Africa, then your tool sucks.
Yeah. Absolutely.
So on ImageNet, especially
the poll images are really bad. There has been an article, I mentioned it at the end, that trained a machine on the people, and you could submit at some point. It was online, it's not online anymore, it's a shame, but you could submit your own image and they would predict what your profession is. And I did it. I think I was a linguist, something like that, but it was completely wrong. And they have also some other example of you could see a series of women images, and they were, definitions that were kind of offensive, I would say. So yeah. So next source of discrimination is the misspecification of a model itself. That's where we get into the deep technical side, I would say. So the idea is that the functional form of a model is different from reality. So there are different possibilities. First, the choice of an imperfect proxy. So you don't exactly you don't know to measure exactly what you want. So you're gonna take another variable, And maybe, let's say, you find that women versus men has a high prediction accuracy. But if you control for income, in an example of credit rating, for example, and you find that women have less credit for worthiness. But when you control for income, actually the relationship reverse, because most women have lower income than men, and if you take for women and men of the same level of income, actually women are more creditworthy than men. So that's just an example, but by choosing the wrong proxy variable, you can introduce gender bias in this example. The choice of target variable also is important. You have, for example, to predict the productivity of an employee. Productivity, it's easy to predict when you have a plant worker, someone who is making like things regularly. But when you have like white collars employees in an office, how do you measure their productivity? It's kind of difficult. So you can say performance reports, but performance reports are by humans, they can be subjective depending on your boss, so on. You can say you want an objective measure, you can take tardiness. If people are really motivated, they should be time every day, all year round. But let's say the company is located in a nice, wealthy suburb, and all wealthy employees are located nearby and then can get to the company very early in the morning, they have no traffic jam issues and so on. People who live on the other side of the city, in the poorer suburbs, they have transportation issues, unreliable public transport or traffic jam and so on. And so you introduce, even though the data seems to be like absolutely objective, it's when the people are badging every day when they get to work. Because of the geography, basically, you can introduce a wrong discrimination. And the last example is with a loss function. A loss function that would fail to penalize for false negative or false positive, or that wouldn't take into account sufficiently the impact of false positive or false negative. And so to remediate that, and we'll talk about that a bit later, there has been a fairness regularizer that have been suggested to augment a loss function to make sure it doesn't discriminate too much. So yeah, the data scientist toolbox. First, we're going to see how to assess the fairness of a model, and then how to design models that are fair, or at least fairness aware. So, if you remember the definitions of discrimination we had at the beginning, this is the first part of the definition, disparate treatment. So that's the situation when protected attributes are present in the data. In this situation, it's quite easy to measure the actual fairness. You can use potential outcomes or counterfactuals to check if the treatment for people who are similar in all attributes but one, the protected attribute, the results are identical. The issue with this method is that actually it's illegal, at least in the US, to include protected attributes in your data and your model. So the issue is like that's the best check for fairness, but that's something that you're not allowed to do. So that means you need to check for disparate. Sorry, yeah.
they can, I think they can use gender. They have gender in the dataset, obviously. But for a number of decisions, they shouldn't base their decision on that. And if you have an algorithm that make a decision like credit for worthiness, recruitment or anything, and someone can demonstrate that they have been refused credit or they have been denied a job because of that, then they can sue you. They can put you into a tribunal and get damages. That's another problem. Explainability is another issue that definitely. But let's say like for most model, you shouldn't base like they shouldn't be included, and if they are included, you're liable to a lawsuit, basically. I don't know if you heard recently, but there was something about the wives of tech people in Silicon Valley, Apple, that were given a lower credit limit on their Apple cards. And the bank said, sorry for that. The bank said that they don't include gender in their assessment. I don't know what happened. My guess is that they use spendings. That's a data they know, and that's a data that can be a proxy for gender, because a woman will have a different spending than a man. So maybe that's how it's been introduced. That's just a guess. Coming back to disparate impact, so the idea is that we don't have the protected attributes in the data. How are we going to assess the fairness of a model? So first, we can check the mean difference between two populations who have the protected attributes and the population that doesn't have the protected attributes. The problem is that differences in results might be due to the protected attribute, but also to other factors. Kamiran and Ali has introduced a metric to try to account for that, which is the unexplained difference metric. So they take the difference between the treatments of two populations, and they try to explain it with all the other attributes that they know of. And then there is, if there is something that is still unexplained, they attribute it to discrimination. The remaining issue is that there might be unobserved confounders. So things that are not in data, but that might explain the difference in impact, and there's no discrimination. So that's really that's actually a real debate. I read a number of articles on that, the fact that there's a kind of catch-22. You don't want to discriminate. You don't want to have protected attributes in the data. But then, if you want to check for discrimination, you need the attributes in the data to check for that. So that's really a catch-22. So now that we know where discrimination might come from, how to assess for it, what's the way to design a model that is at least a bit more fair than normal? The first step, and the author insists on it, and I insist even more, it's that the data science process should be informed and with regular discussions with domain, law, and ethic experts. Data science shouldn't try to resolve this issue by himself, basically. And then at each stage of the process, they can use discrimination-aware test. So if we take the process, so that's a bit more detailed than the one we saw before, but you can see that you have discrimination data unit test based on the raw data that can identify a discrimination potential or not. if you have a discrimination potential, you can do pre-processing of your data to try to remove it at this stage. Then when you train your data, train your model based on the data, you try to have a loss function, for example, that is fairness aware, so that it takes into account discrimination. Then you assess your model, classifier, unit test for accuracy and discrimination. So there's always these two metrics, basically. And then you can also, in post-processing, try to reduce discrimination. So to get into, yeah? Yeah, I guess yes. It's just that they try to to specifically introduce discrimination unit test at each stage of the process. So what does that look like in more detail? So at the stage of exploratory analysis, obviously we need to check for existing discrimination in the data, check for variables that might have high correlation to protected attributes. So for example, in the US, you have code. Or the zip code could influence your credit worthiness by itself, it's not clear. But in fact, the zip code encodes your race in the US. So that's a problem. And then check data for under or over representation, obviously, for each protected group. Pre-processing. So once you check your data, you can try to remove the underlying discrimination existing in the data. So that can involve relabeling the data, resampling the data, or reweighting the data. I think we did an example of resampling when we did the sentiment analysis, because there were too few positive sentiments, and so we generated more to have a balanced data set. So that's basically the same idea. And then in processing, the idea here is to penalize the discrimination when training the model, and so in adding a fairness regularizer to the loss function. So that's a geometrical representation from Kamishima, Akao, Aso. The complete reference at the end of the slide. You have the true distribution and the estimate distribution. That's basic machine learning, right? But then you have a subspace of fairness. What would be a fair distribution in the real world? And then you try to, what you need to arrive, it's a fair estimated distribution. So to kind of have a cross between the estimates and the fairness model. I don't get more into technical details. You can read the article to see the mathematical functions that they derive. But that's the main idea. There are also post-processing methods, but they are not detailed at all in this article, and I didn't go looking for them. Can you, yeah. Yeah, so what you mean is that yeah. Okay. Yeah, but that's a question of balance and yes. yeah, that's the trade-off. Yeah, yeah. But that's the constant trade-off, and yeah, I can't talk about it right now, but you have a trade-off obviously between accuracy and fairness. That's inevitable, unavoidable, because the world, it's, yeah. Maybe you're not, yeah. Okay, yeah. Okay. Yeah. The question now is how to assess fair. So the idea is, like, that's the definition of fairness from the beginning, and uh, my take on this, I don't know how it works in chemistry models and so on, but uh, that fairness is kind of a moral, philosophical issue in the end. And I'm not, well, yeah, that's I'm not sure a model can be fairer in that sense, because in a way it's always a moral decision in the end that you have to take rather than a mathematical one. We'll get to that maybe in the discussion. So to sum things up, the different at each stage, exploratory analysis, pre-processing, in and post-processing, there are different techniques that the data scientists can use, and at each step continue to engage with domain experts and decision makers to make sure that the choices that are made are in line with ethical choices, basically. Because that's not only technical decisions, it's also political and ethical decisions. So that's more personal comments, but I touched on that. There is an unavoidable trade-off between accuracy and fairness. If we want to measure the accuracy of a model against the actual world, which is discriminatory, and we want to build a better world, well, the model is not going to be as fair, as accurate. A fair model won't be as accurate. If we say accuracy is you match exactly the current world. So in this sense, the decisions are not only technical, but first and foremost political and ethical. That means that there is a point where you need to decide, do I go for accuracy, do I go or it's not completely black and white, it's more a gray area, which balance, how much we tweak the model, which balance do we find between accuracy and fairness. Debate on? Yeah. Yes, well, that's why I included the decision makers, but in the end, that's also the responsibility of a data scientist as a designer, I would say, an engineer. There is a moral responsibility of what you're putting out there, especially because the responsibility is at the scale machine learning models are implemented, and they are now impacting like billions of people. 4.5 billion internet user estimated today. So if you think like it's a huge impact, it's a huge responsibility. So yeah, I would advocate to share this responsibility across not only data scientists, but decision maker, business, and law experts and ethical experts. And it ties to the larger question of algorithmic governance. So I won't go into that, but just to say that in, I think in Australia, there is I don't know if it's a machine learning model, but they have implemented something to check whether the benefits, the social benefits that people receive are correct or not based on their income. And there have been a large number of errors made. It was automatic. It is still automatic. I think it's still in place. A huge number of errors. People receiving notice that they have received benefits, too many benefits, and they need to reimburse the government and so on. People who, of course, are poor in the first place and are placed in very difficult positions. And in the end, it's the algorithm that is wrong. The governance here is that in a non-algorithmic society, this decision is made by humans. You can go and talk to humans in the benefit office and try to reverse the decision, and it's not automatic. Now algorithm decide. There is no human involvement at all in the process. They take the data from one place, they match it with the data from another place, and then a letter is sent, and the money is blocked without any human involvement. So that's the idea of algorithmic governance. Algorithm manage our life before it was human decisions. It was inefficient, maybe. It was certainly less productive. Also prone to errors, but maybe less larger possibility for people to get involved and to rectify in case of error. So to go further, because that's only very quickly on the subject. There are other definitions of fairness. Like you mentioned at the beginning, it's an ongoing debate, and there are multiple metrics that have been suggested. More attributes could or should be included also. Like we specified a number of attributes based on what's illegal in the US, but that's not all possibilities of discrimination. We looked at discrimination and fairness at the group level, but not at the individual level. And that's also very important. And that's another completely different issue. We also check for fairness for each attribute separately, but not for an individual that would have a constellation of different attributes. Black women with poor income, or I don't know. So it's the intersectionality issue. Explainability of decisions, you mentioned it. We don't like basically deep learning models are black boxes. We don't really know how to interpret the results of these models, but this decision, the reason for these reasons matter actually for individuals. They want to know why this decision has been applied to them. And it matters also for companies because they are liable. Typically, the bank, we mentioned the bank that provide the Apple cards. They said, oh, no, we didn't use sex in our data to predict and so on. But still, the Wall Street regulator opened an investigation on them. So I don't know what's going on, but there are the possibility that they are going to be penalized for this if they found a significant discrimination against women, even though the sex is not present in the data. Last, use of causal Bayesian network. It's an idea as I saw in an article by authors from DeepMind. The idea is to be able to make a model of the data and the causality relationship between all the variables. So you can try to predict if it's actually discrimination or not. There is the reference of the article. Where is is it? Yeah. CHAPA is a causal Bayesian network, a flexible tool to enable fairer machine learning. So that's some of the articles I use. So the first one is the main one I followed for the presentation. Kamishima is the one where there is the regularizer functions. Zelak also has some regularizer and then the loss function, augmented loss function. The causal Bayesian network, weapons of mass destruction. Cathy O'Neill is one of the author of the article, and she wrote a book from 2017 where she goes through all the examples I gave at the beginning and others in much more details. There's a new book, I haven't read it yet, but from Kearns and Ross Aaron, the ethical algorithm, where they detail this into much more details. There is a talk on YouTube with Lex Friedman that's really interesting too. And the last one is what I told you about ImageNet, and ImageNet actually there is a whole set of bias and discrimination and issues with ImageNet, especially for the people subsection. So it's working fine with cats and dogs basically, but people it's and I think they even took out the people section now. It's not even available anymore because there were too many issues. So let's start the discussion. We already have some discussion, but do you have any personal experience related to this? Do you know about the laws that apply in Switzerland? Because we talked mostly about the US. And what else do you think could help, or what's your take on this? Okay. Well.